Differentials. In this section, we're going to learn another application of derivatives. Tangent line approximations. Suppose function f of x equal x to the fourth power. Let capital T of x be the tangent line at 3,81 as you see the graph below. Find the equation of tangent line capital T of x. So to find the equation of a tangent line, we need the slope and a point. We are already given a point 3,81. So to find the equation of this tangent line, all we need is now to find the slope, and slope can be obtained by finding derivative of f of x, as you know. So f prime of x is equal to, take the derivative of x to the fourth power, I get 4x to the third power, and slope of this tangent line at 3,81 will be f prime of 3. So now plug 3 for x in f prime function. You get 4 times 3 to the third power, which is 4 times 27, and it is 108. So now, to find the equation of a tangent line, let's use Poinslow form of a line. And Poinslow form of a line was y minus y1 equal slope m times quantity x minus x1. And your point 3,81 is your x1, y1. And you found your slope m, which is a 108. So plug it in. Our equation of a tangent line becomes y minus y1 is 81 equal slope 108 times quantity x minus 3. Distribute and solve for y. You will get y equal 108x minus 243. So your capital T of x is equal to 108x minus 243. Now let's suppose we zoom in at the point 3,81 right there, and we came here. Let's calculate each value in the table. I have a table below. My x values are 2.9, 2.993. X values are getting closer to 3 from the left. Now, if you go from the bottom, I got 3.1, 3.01, and 3, so that the x values are getting closer to 3 from the right. And what we want to do is, for these each x values, we want to calculate function values, and also what would y values be if we were to plug these x values into tangent line and actually find out their differences is what we're about to do here. So first, if I plug all these x values into my original function, my y values becomes, first one is 70.7281. All you're doing is you're plug it in here and get 2.9 to the fourth power. That's what you're going to do. And if you do that with the 2.99, you get 79.92539. And if you plug 3 in there, you're getting 81, 3 to the fourth power. You plug 3.01, I'm getting 82.08541. If you plug 3.1, I do get 92.3521. And same x values, if I plug them to tangent line equation instead, I do get 70.2, 79.92, same 81, 82.08, 91.8. If we subtract them, bigger function value minus smaller function value, their difference is 0.5281, 0.00539, No difference, of course, for the point that they are shared by both the functions, 0.00541, 0.5521. So you can see here that as x gets closer to 3, whether it is from the left or the right, the difference of y values between the original function and the tangent function gets smaller. So the whole point here is, as x gets farther away from the point of tangency you get, the error gets worse. So tangent line approximation is used a lot of time to approximate the function value, and it will be ideal if that point of evaluation is really close from the point of tangency. Okay, so let's learn what the differentials is. So look at this first point, x comma f of x, on your function and on your tangent line. If we take delta x as an increment of x and move to the right-hand side of x, so we obtain another point as x plus delta x, comma, f of x plus delta x. And if we take the same x on your tangent line, this point will be another point on my tangent line here. From x to x plus delta x, increment is delta x as you see. Now, what is the increment of y when you change from x to x plus delta x? That will be the actual change using your function value. It will be your y2 minus y1. So delta y, which is the actual change in y's, which would be f of x plus delta x minus f of x. Now let's look at the original point and the next point on your tangent line with the same increment of x. You can see the change in x is still exactly same amount in original function, which is dx. So change in x using tangent line is exactly equal to the actual change in x in our original function. However, you can see that approximate change using tangent line, which is dy, is not equal to the delta y, which is the actual change using function. You can see delta y is this much and dy is only this much. They're not the same. However, in differentials, we use dy to approximate the delta y because dy is approximately equal to the delta y as delta x gets smaller. So note that dy is approximately equal to delta y. So to approximate delta y, we will use dy. Now, to calculate the slope of a line, we always did y2 minus y1 over x2 minus x1. From this graph, you can see y2 minus y1 is dy over x2 minus x1 is dx. And that is equal to our slope function, f prime of x. So simply, you can find the dy by multiplying dx both sides, and you can get your differential of y is equal to f prime of x dx, and is called the differential of y. So differential of y is dy, and it is equal to f prime of x dx, which is approximately equal to delta y. In next example, we're going to calculate delta y and dy to compare how close they are. So let's say our function is x squared plus x plus 1, and x is 2, and delta x is equal to dx, which is 0.1. First of all, let's calculate delta y. Remember, delta y is exact change in y values using your original function. So it is f of x plus delta x subtract f of x. And right now, our x is 2 and our delta x is 0.1. So in our case, delta y is equal to f of, recall x is 2, delta x is 0.1. So this is 2.1 minus f of x equal 2. So it's a f of 2. And you're going to evaluate your f at x equal 2.1, which is 2.1 squared plus 2.1 plus 1. When you do that, you get 7.51 minus f of 2 is 2 squared plus 2 plus 1, which is 7. So delta y is 0.51. And remember, this is the actual change in y value from 2 to 2.1 in x. Now, let's calculate dy. What is our dy? dy could be calculated by f prime of x dx. If you forget what the dy was, just quickly write dy dx, which is equal to f prime of x, and then you can multiply both sides by dx. So then you go, oh, that's right, my dy is equal to f prime of x dx. So you can recover that, all right? In our case, our dy is equal to f prime of 2 times dx. And f prime of x is equal to, take the derivative of x squared plus x plus 1 here, we get 2x plus 1. So f prime of 2 is equal to 2 times 2 plus 1, which is 5. So it is equal to 5 times, remember dx is exactly equal to delta x all the time, so that's a 0.1. And when you multiply, you get 0.5. And what is this? This is approximate change in y values from 2 to 2.1 in x values using tangent line. And this was actual change using original function. So what do you think? It's not too bad, right? Original change in y's values from 2 to 2.1 is 0.51. And if you use tangent line approximation, dy, approximate change in y values is only 0.5. Their difference is 0.01. Not bad at all. All right, let's find the differential of each function. Since dy is always equal to f prime of x dx, all you have to do is find the derivatives of each function and attach dx to it. So what's the y prime here? That will be 2x. So differential of y for this guy is 2x dx. Second one, I want to get the y prime, and because it's a product of two functions, you have to use product rule. Take the derivative of x, you get 1 times sine of 3x plus x times derivative of sine 3x. And since the sine 3x is a composition of a function, I need to use a chain rule. Derivative of sine is cosine of input times derivative of inner function is 3. So then differential of y is bracket sine 3x plus 3x cosine 3x times the dx. So I found the differential of y. The third function is rational function. So to take the derivative of this one, I would need to use quotient rule. So let's use quotient rule to take the derivative of a third one. Y prime is equal to low quantity x cubed minus 2 times d high derivative of x squared plus 1 is 2x minus high, my high is quantity x squared plus 1 times the low, derivative of low is 3x squared over square below. So I need to square the quantity x cubed minus 2. When you simplify this, let's distribute. I get 2x to the fourth power minus 4x. I'm going to distribute the negative here. And I'm also going to distribute the 3x squared from the right as well. So minus x squared, 3x squared, when you multiply all of them, you get negative 3x to the fourth power. Distribute the negative to 1 and distribute 3x squared, then you get negative 3x squared over quantity x cubed minus 2 to the second power, which is equal to, when you simplify, 2x to the fourth power minus 3x to the fourth power gives me negative x to the fourth power minus 3x squared minus 4x over x cubed minus 2 to the second power. If you factor out the numerator, since the fourth term is negative, you should take the negative GCF out. And I'm going to take the negative x out. Open x to the third power plus 3x plus 4 over quantity x cubed minus 2 to the second power. All right, differential dy then is equal to negative x, quantity x cubed plus 3x plus 4 over quantity x cubed minus 2 squared dx. So I found my differential of y. So now we learned that delta y is equal to f of x plus delta x minus f of x. So by adding both sides by f of x, we can get f of x plus delta x equal f of x plus delta y. So to find out f of x plus delta x, I could approximate this by f of x plus, and we just learned that delta y is approximately equal to dy. But dy was always equal to f prime of x dx. So if you already know f of x, you can approximate f of x plus delta x by just adding f prime of x times the dx. And dx is always equal to delta x. So we are going to now use the fact that f of x plus delta x is approximately equal to f of x plus f prime of x dx to estimate a function value. So let's approximate square root of 24.8 using differentials. The fact you are going to use is f of x plus delta x can be approximated by f of x plus f prime of x dx. So first of all, you got to identify what your function is. And because you got square root of something, your original function will be square root of x, which is x to the 1/2 power. And then from the formula below, you can see that you're going to need f prime of x. So find out what the f prime of x is. That will be 1/2 x to the negative 1/2 power, which is equal to 1 over 2 square root of x. Now, what you need here is a known value of f of x that is very close to the problem that we're about to approximate, which is square root of 24.8. What is the known value of square root of something that is very close to square root of 24.8? And this will be x plus delta x, Remember, delta x doesn't have to be positive number. So what you want to do is find the x that is very close to 24.8. You don't want to make delta x positive, so you don't want to choose x equals 16 versus x equal 25. Remember, as delta x is smaller, your approximation is going to get more accurate. So therefore, we want x to be 25 here. So choose x equal 25. Then delta x will be negative value, since you need to add negative 0.2 to get 24.8 from 25. And remember, delta x is always exactly equal to dx. So we are ready to approximate it now. F of 24.8 is f of x, your x is 25, plus delta x is negative 0.2. You can see they add them up to 24.8. This will be approximately equal to f of x is 25, plus f prime of x is 25, times dx, and your dx is exactly equal to delta x, which is negative 0.2. And f of 25 is square root of 25, plus f prime of 25 is 1 over 2 square root of 25 times negative 0.2. And you can let calculator take care of the rest. This is then 5 plus 1 over 10 times negative 0.2, which is approximately equal to 4.98. So you approximated f of 24.8 knowing the f of x and f prime of x and dx. This will be on the test, so make sure you know how to do it. Use the differentials and graph of f to approximate f of 2.96 and f of 3.1. So again, what we know exactly close to 2.96 is f of 3 and f of prime of 3. So what's f of 3 here? F of 3 is 2. And what's f prime of 3? You can just find the slope of this tangent line using exact 2 points. So f prime of 3 is equal to, I have exact point here and another exact point here. You can do rise over run, which is 1 over 2. So f prime of 3 is 1/2. So then f of 2.96 is equal to f of, I want to use the 3 plus, my delta x will be minus again, which is negative 0.04. Then this can be approximated by f of 3 plus f prime of 3 times the dx, and dx is equal to the delta x, so that will be negative 0.04. Now use all the points above that we already calculated. F of 3 is 2 plus f prime of 3 is 1/2 times negative 0.04. You get 1.98. Yeah? Pretty easy now, right? And we also need to get f of 3.1. And f of 3.1 is f of 3 plus, this time our delta x is positive, 0.1. So this can be approximated by f of 3 plus f prime of 3 times dx, and dx is equal to the delta x, and delta x is a positive 0.1, which is f of 3 is 2 plus f prime of 3 is 1/2 times 0.1, which is approximately equal to 2.05. So here's our approximation of f of 3.1. Okay, this is everything in section 3.9. Hopefully, you understood the concept of how we could use differentials to approximate function values.